Hello everyone, welcome to my civil engineering YouTube channel. Please subscribe to this channel and hit the bell icon to get notified when I post my new videos. So today I'll be discussing how to determine moment of inertia for a semicircle using the method of integration. So here basically this concept, that is determination of moment of inertia for a semicircle, in this concept, I have assumed the centroidal axis to be parallel to the diameter. So, this moment of inertia is calculated about the centroidal axis, so which is assumed to be parallel to the diameter. That is nothing but the centroidal axis is assumed to be in the horizontal direction. So, I have considered a semicircle of radius equal to capital R, so which is as shown in the figure. So I have also chosen a elementary section, so wherein it is represented by the shaded portion over here, and theta represents the angle made by the elementary section with reference to the horizontal axis, and dr represents the radial width of the elementary section, and r represents the radial distance of the elementary section from the center of the semicircle, and capital R represents the radius of the overall semicircle, and G represents the centroid of the semicircle, and d theta represents the angle, internal angle subtended by the elementary section. This is the d theta. So therefore d theta represents the internal angle subtended by the semicircle. So here I need to find out what is the moment of inertia for the elementary section primarily. So for that, as I said that the elementary section, if I just consider dA as the area of the elementary section, so dA is nothing but the area of the elementary section, wherein if I just consider the semicircle as a whole, compare it to the area of the semicircle as a whole, so this elementary section is very small, so the curvature of the section could be neglected, so therefore it could be treated as the rectangle itself. So therefore the area remains as length into depth, so therefore the length is assumed to be as r d theta, and depth is nothing but dr, so therefore it is dr times of r d theta, dr times of r d theta. So next, coming on to determination of moment of inertia for a elementary section. So as I stated that this dotted line represents in the elementary section, this dotted line represents the centroid of the elementary section. So in order to determine the moment of inertia for the elementary section with reference to horizontal axis, I need to consider the centroid for the elementary section, so which can be taken as area into the square of the perpendicular distance. So if I just take horizontal as a reference axis, the perpendicular distance will be in the vertical direction, so therefore y is the perpendicular distance of the elementary centroidal axis with reference to horizontal axis, so therefore it is dA times of y square. Moment of inertia for elementary section could be considered to be as dA into y square, but as we know that y is equal to r into sine theta and x is equal to r into cos theta by the trigonometric by the knowledge of trigonometry, so therefore it can be taken as dA into r sine square theta, but also r dA into r sine theta the whole square. But we know that dA as dr into r d theta, so if we substitute that value in place of dA, it would be equal to r d theta into r sine theta the whole square. So this is the representation of moment of inertia for the elementary section. Next, coming on to the next concept, that is by using the moment of inertia for the elementary section, we need to find out the moment of inertia for the overall section as a whole. So basically I just consider a axis for a reference, before finding the moment of inertia for the centroidal axis, I just take some axis as a reference. So for that I am choosing AB as my reference axis. For that I am choosing AB as my reference axis. So I just repeat it once again. So before going to find the moment of inertia for the overall semicircle, so with reference to the centroidal axis, I need to choose some axis as a reference. So for that I am going to choose AB as a reference axis. So in order to determine the moment of inertia for AB, so the same procedure or the same equation of the moment of inertia which I had found out for the elementary section, I need to integrate with reference to 0 to pi. I need to integrate that since we have two variables, that is theta and d theta and dr. So therefore we are supposed to integrate with reference to theta first with the limits of 0 to pi, and then we are supposed to integrate the r with reference to the limits of 0 to capital R, that is 0 to radius. So after all simplification, I will get the value as pi r power 4 by 8. Pi r power 4 by 8. Since I just repeated, since we have two variables here, so one is d theta and dr, so therefore we are supposed to do the double integration procedure. So wherein with reference to theta we are supposed to integrate between the limits 0 to pi, and wherein with reference to the r we are supposed to integrate with reference to the limits 0 to r. So therefore we are supposed to double integrate the equation. So after integrating all the things, we will finally arrive at the equation as pi r power 4 by 8. So pi r power 4 by 8 is the value of IAB, that is moment of inertia with reference to the base axis AB. So coming on to next important step, that is moment of inertia with reference to the centroidal axis. So first thing, in the previous slide, as I have explained that we have taken the base as the reference axis. So in order to determine the moment of inertia with reference to centroidal axis with base as reference, so we are supposed to use the parallel axis theorem. So before going to that, I just assume this as a centroidal axis. I just assume this as a centroidal axis, which is represented by this blue color line. So by using the parallel axis theorem, so it is the nothing but the equation goes on like IAB, that is moment of inertia with reference to AB axis, is equal to IXX plus AY square or AY bar square. So here IXX plus AY bar square. So wherein Y bar represents the centroidal distance of the semicircle with reference to XX or the horizontal axis, with reference to XX as a reference axis, or with reference to the horizontal centroidal axis. So as I know that IAB, I have got the value from the previous slide, that is pi r power 4 by 8, and IXX is unknown, wherein I need to determine that, and area of the semicircle is pi r square by 2, that is the area of the circle, as we know that pi r square. So semicircle will be half of the area of the circle, therefore the area of the semicircle is pi r square by 2, and then by using the centroid derivation, so we had came across the centroid of the semicircle as 4r by 3 pi. 4r by 3 pi is the centroid of a semicircle with reference to horizontal centroidal axis. So if we just substitute these values, we'll get the value of IXX that is moment of inertia with reference to x axis, or moment of inertia with reference to horizontal axis with base as the reference axis, as 0.11 r power 4, 0.11 r power 4. So wherein capital R represents the radius of the semicircle. Capital R represents the radius of the semicircle. So here, as in case of semicircle, here, so firstly we are going to assume the elementary axis, and from the centroid of the elementary axis we are supposed to find out what is the moment of inertia for the elementary axis. So by using that equation we can find out what is the moment of inertia with reference to base axis as a reference for the overall semicircle, that is IAB we have found out. So wherein AB was the reference axis. So by using the IAB value and by utilizing the parallaxis theorem, so we had found out what is the moment of inertia for the centroidal axis, that is XX. So IXX finally we have got it as pi 0.11 r power 4, 0.11 r power 4, wherein r represents the radius of the semicircle. Thank you for watching. Please like, share and subscribe the video. Thank you.